All right, so the next topic is going to be brief. We're going to discuss the proof of the area theorem. So what I decided to do is just to sketch this. There's some GR that I need to cover that we're going to need anyway. So we'll start by doing a little bit of GR, and then I'm going to sketch the proof of the area theorem. So let me remind you where we are in terms of black hole thermodynamics. We said that if you postulate that the entropy of a black hole is the event horizon area divided by 4 in Planck units, that black holes obey the first law of thermodynamics. Now, when we first checked this, we didn't have a good reason to call T the temperature. It was just the surface gravity. But then we went through and showed that T really is truly a temperature. It's the Hawking temperature. So we've pretty much covered the first law in all its parts. And now we're turning to the second law, which is the area theorem. So before we do the area theorem, I want to discuss quickly some things in GR that you may or may not have seen. The first one is hypersurfaces. So I just want to introduce some geometry quickly. The setup for this discussion is that we have a manifold M, which is d-dimensional, and on that manifold we'll have a coordinate x and a metric g. And then somewhere in that manifold, okay, so that manifold is the board, let's say. And then somewhere in that manifold we have a hypersurface, which is a codimension 1 submanifold. We'll call that sigma. So sigma is dimension d minus 1. And on sigma, we have a coordinate y. I'll use the indices ij for this coordinate, and a metric hij. So the way to specify this embedding of a hypersurface into the bigger manifold is to draw at each point on the hypersurface, we draw the normal, which I'll take to be a unit normal, and then we pick a basis of tangent vectors. Call those E1 alpha and E2 alpha. So those are, since those have an alpha index, those are being viewed as vectors in the big manifold. Vectors, everything in the big manifold has alpha beta indices, everything in the little manifold has ij indices. Okay, so we have a normal and alpha with n squared is plus or minus 1, depending on whether this hypersurface is space-like or time-like. And we can view these tangent vectors as defining for us a projector E alpha I. Okay, so the lower index, the 1, 2, that's one of the ij indices that live in the submanifold. And E alpha I is dx alpha dyi on the submanifold. And this is chosen to be tangent. That is, if we dot it into the normal, we get 0. that also shows that it's a projector, in the sense that if we take any vector in the big manifold, and we, well, yeah, just because it's dotted into the normal as 0. Okay, so suppose that, just to make this concrete, I'm going to suppose that sigma is space-like. So n squared is, and I'll take the full manifold to have a Lorentzian signature. So the normal is time-like. And we could, of course, do this for any choice of signatures. I'm just doing that to make a choice, to make this concrete. And then we'll decompose the metric as G alpha beta is H alpha beta minus N alpha and beta. So the way you should think of this is that this is like the space piece of the metric, and this is like the time piece. Now, if you think about doing this to Minkowski space, then you're just going to drop off the TT component of the metric. So this defines H alpha beta. And by construction, H is transverse. That is N alpha, H alpha beta. You can dot it into that, and you'll find that it's 0. So H alpha beta is a projector onto things that are tangent to the submanifold. That is, given some vector V alpha, we can project it with H, and this, so if we call this V tilde alpha, then this will be tangent to the submanifold because N alpha V tilde alpha is 0. And similarly for higher tensors. Okay, so I'm going through this sort of carefully. The thing to notice is that there's different ways of thinking about vectors that live on the submanifold. You can think of them as vectors with ij indices that actually are d minus 1 dimensional vectors that are associated to the submanifold. Or you can think of them within the bigger manifold. Then they have alpha beta indices, but dotted into they dot into the normal and give 0. Okay, so there's different ways of thinking about these vectors, and similarly, there's two different ways of thinking about the metric on the submanifold. You can think of it as a d minus 1 dimensional metric. That's hij. Or you can think of it as this H alpha beta, which is a bigger matrix with an extra component, but it has, since if we solve this for H, well, since this dots into N to give 0, this thing has rank d minus 1. Okay, so this is a degenerate metric in d dimensions, it has rank d minus 1. The induced metric on the submanifold is Hij, is Ei alpha, Ej beta, H alpha beta. Sorry, G alpha beta. I think it's both, actually. Let me write it this way. So that's the sense in which these E's also act as projectors. They map you from tensors in the big manifold to tensors in the little manifold. To check this fact, we just calculate the line element ds squared restricted to the submanifold. So this is G alpha beta, dx alpha, dx beta. And now we do the change of variables from x to y. It's G alpha beta, dx alpha, dyi, dyi, dx beta, dyj, dyj. And that is, well, these derivatives here are the Ei alphas. So this is, as claimed, Hij, dyi, dyj. Questions so far? Very sort of fast, just formalism. Good. Okay. It's a useful formula is for the inverse of that relation there. Okay, so. The formula is H alpha beta is Hij, Ei alpha, Ej beta. That you can, let me make an exercise, but you can derive this from this relation here. But the reason it's useful to remember this formula is that, of course, this is not equal to H alpha beta inverse. Because that's not an invertible metric. Okay. Now I can define what I'm trying to get to here, which is the extrinsic curvature. Okay, so the extrinsic curvature is Kij is defined as Ei alpha, Ej beta, grad alpha, n beta. Let's see. So n here, this is a little tricky because there are many different. Every source gives a different definition of the extrinsic curvature. If people are being careful, they're all basically equivalent, but slightly different. In this case, note that n is really only defined it's a vector in the big manifold, but it's the normal vector, so it's only defined on the hypersurface. And this involves taking derivatives of that vector. Okay, so I've done something slightly illegal here by taking derivatives of this vector off the hypersurface. But actually that's okay. We can extend this arbitrarily off sigma. And the reason it's okay is because then we project back onto the hypersurface and the extension will drop out. Okay, so you can check that this is independent of how you extend it off the hypersurface. Another definition formula that people use for the extrinsic curvature is k alpha beta is a half of the Lie derivative along n of h alpha beta. So this is the Lie derivative. Which you can also write as a half of h alpha mu h beta nu of the Lie derivative along n g mu nu. And I'm going to write two more useful formulas for this. So the first one is that, let's see, so, well, let me write the formula. It's just a half Lie n of g alpha beta. Now this is not quite the same. This is true if so this one is true in general. For this one, I've chosen to extend n off the hypersurface along a geodesic. This simplifies the formula a little bit. And finally, we can also write that as the symmetric derivative, grad alpha and beta. That one also requires n to be geodesic. Okay, so just writing a bunch of useful formulas up here. The thing to remember is that no matter how you write it, the extrinsic curvature is really a tensor that lives on the submanifold. You know, I've written it. You can give it indices in the big manifold, but it's been projected onto the submanifold. Okay, so it'll be if you dot it into the normal, you get 0. Or you can just write it as intrinsically living in the submanifold, like I've done here with the ij indices. Either way, it's really something that lives in the submanifold. Let's look at the trace of this tensor. So the trace is often just called k. You can calculate the trace using either of these formulas. You can think of it as trace of the kij, or you can think of it as k alpha alpha. Those traces are the same, and they give grad alpha and alpha. And good. What else do I want to say? Okay, so I call this thing the extrinsic curvature. So probably you already know what it means, but let's think about the interpretation. So usually in GR we talk about intrinsic curvature, like Ricci, Riemann, etc. There's all intrinsic curvature. And usually the first thing that we tell you when we teach you GR is that, I know the first thing I say is that this is not curved. Okay, that's not intrinsic curvature because all of the angles on my graph paper that are hard to read there are still right angles. That's extrinsic curvature. Okay, so extrinsic curvature tells you it's not a property of a submanifold, it's a property of the embedding. So it's telling you how this is a flat two-manifold, and it's embedded in R3. Right now, that embedding has no extrinsic curvature. Well, now the embedding does have extrinsic curvature. So that's what extrinsic curvature is. We can see that from this formula for the trace. Well, this is going to tell us about the trace. So like, say you have a manifold that's sort of shaped like, that's an embedding that's sort of shaped like this, and you calculate the normals. So those normals are converging, and so the divergence there will be negative. So k is less than 0 for an embedding like this. The important thing to note here is that it depends on an orientation. It depends on a choice of orientation. Of course, if I had drawn my arrows going outward, then we would have concluded that k is greater than 0. So there's a choice of normal, and the orientation is important. Questions? So I should mention references. So there's an appendix in Carroll on hypersurfaces. If I remember correctly, the original edition of the book doesn't make a whole lot of sense in that appendix, but the latest edition is good. If that scares you a little bit, then you can also look in Poisson, who goes through this in great detail and is very careful about whether something is an IJ index or an alpha beta index, et cetera, and uses the same notation that I'm using here, I think. Okay, now I want to prove an identity that's important for interpreting this extrinsic curvature. So, well, let me draw a picture first. Okay, so this is our submanifold sigma, and let's say it has volume delta V, and then we're going to evolve this in time. Okay, so at each point on the manifold, you follow a geodesic along the normal. So you head out along the normal for a time delta tau on each point on the manifold. So you do that here, do it there, do it over here, etc. Okay, and that gives you a little bit later a new manifold. So at each point we've just gone forward in time by an amount of proper time delta tau. Then the claim is that k, the trace of the extrinsic curvature, is 1 over delta v, d by d tau of delta v. It's telling you how fast volumes are evolving in time. Maybe a more explicit formula here is that k is 1 over root h, d by d tau of root h, where h is the induced metric on the hypersurface. This makes a lot of sense given the pictures that we were just drawing. So those pictures over there of the convergence or divergence of the normal vector. If the normal vector is converging, then the hypersurface is getting squished. If it's diverging, the hypersurface is stretching.
So is delta V some small volume element around the point?
Yes, that's right. Yeah, this is all being done infinitesimally, so I've defined delta V at a point, and this whole thing you should think of as infinitesimal. So let's prove this. There's a covariant proof in Poisson that takes like 4 pages, or you could just choose coordinates locally and save yourself a lot of trouble. So locally, you can choose ds squared is minus d tau squared plus hij of tau dyi dyj. Okay, so tau is proper time in the tau direction, and hij is the induced metric on the hypersurface. And the normal n is obviously just the unit vector in the tau direction. And then we just calculate 1 over root h, d by d tau of root h is a half hij d by d tau hij. I've just used the formula for the variation of the determinant. This is a half hij times the Lie derivative along n of hij, which is trace k. That was one of our formulas for k that we had a minute ago. Okay, so I picked some coordinates along the way, but at the end of the day, this is a covariant expression. Tensors on the left, tensors on the right, so this formula is just true in general. This also, by the way, is okay. Pretty much every time in my life I've ever calculated an extrinsic curvature, I've done it this way. You can't quite always do this, or it's not always convenient, but it's pretty much always done this way. So typically you choose coordinates that are adapted to your hypersurface. So that your hypersurface sits at some fixed value of one of the coordinates, in this case tau. And if you can write the metric this way with the hypersurface at some fixed value of tau, then extrinsic curvature just means the derivative of h in the tau direction. Okay, so in practice, calculating extrinsic curvatures in some coordinate system usually just amounts to picking a good coordinate, and then it's the derivative of the induced metric. Okay, so now I want to introduce the concept of a congruence. I'm not going to talk about congruences in much detail in this class. You can read about them in Poisson or in Wald, but I want to give just enough flavor of what a congruence is, and in order to give you just enough flavor of how the area theorem comes about. Okay, so our first example of a congruence is going to be obtained from a hypersurface. Okay, so if we have a hypersurface, then we can define these normals on the hypersurface, everywhere on the hypersurface. By the way, all these hypersurfaces, they just have to be some open set. They don't have to extend all the way to infinity or anything. They can really just be a patch of a hypersurface like this one, because everything we've been saying has been local. Okay, so we pick a local hypersurface like this, and there's a normal vector field n, and what we're going to do is we're just going to extend n off the hypersurface following geodesics. Okay, so maybe that looks something like this. So extend n along geodesics. You could either think of this as defining a vector field in some patch of spacetime, or you can think of it as defining for you a collection of curves going through this patch of spacetime. And this is a special example of a geodesic congruence. So more generally, a congruence, I'm not going to write the definition up because we're not going to use it, but I'll say it for you. A congruence is a collection of curves on some region in spacetime such that exactly one curve goes through every point. Say it again. You have some region of spacetime, exactly one curve goes through every point. Okay, so in other words, it's a nice smooth collection of curves that do not cross each other or anything funny like, they don't end or cross each other or anything like that within that patch. Okay, so this is defined as some open region of spacetime. Now, this is what makes this a special example is that this, because of the way we've defined it, this is a hypersurface orthogonal geodesic congruence. That is, there exists a hypersurface, at least at time 0 here, there exists a hypersurface for which this is the norm. Not every congruence is hypersurface orthogonal. Should I draw a picture? Not every congruence is hypersurface orthogonal. to give you an example, let me take two hypersurfaces like this. Okay, so there's a hypersurface orthogonal congruence that just kind of goes straight up through these two things. But if I draw one that's kind of twisty, like this, and so on. I shouldn't be drawing it just on the edge. I really want a patch of space-time, so I'd have to extend this into the interior. But we could do that. And this is a congruence. It's a set of curves that don't cross each other, but it's not hypersurface orthogonal. There is no hypersurface that would have this twisty normal. This is formalized by something called the twist, which we're not really going to have occasion to use, but if you see people talking about the twist or read about this in Wald, then that's measuring this twistiness. And a congruence is hypersurface orthogonal if and only if the twist equals 0. Hypersurface orthogonal if and only if this vanishes. Expansion of a congruence is theta is the divergence of the normal vector. That's the same as trace k. That remember we were just talking about trace k. It was the same formula if it's hypersurface orthogonal. So in our case, we can think about either of these, but the equations that I'm going to write, people always write in terms of theta and think of it as the expansion, so I'm introducing that different name for it. And recall that we just showed that this is 1 over root h d by d tau of root h. So the expansion is just what it sounds like. It's telling you how fast hypersurfaces are stretching or shrinking as you follow them along geodesics.
This is the same quantity that's used in cosmology to talk about expansion of the universe, right?
It's proportional to that. I can't remember if it's literally the Hubble expansion. It's proportional. Yeah, maybe it's literally the same. Yeah. Okay. Okay. So this has just been some GR, and now I'm going to turn to the proof of the area theorem. So the proof of the area theorem relies on one more equation that I need to introduce. So this one, I decided not to give a detailed derivation of this equation, just because it would lead us sort of far afield, and we're not gonna use this again. This is the Raychaudhuri equation. let me write the equation, and then I'll tell you what it means. Okay, it's an equation for d theta d tau, and on the right-hand side is minus 1 over d minus 1 theta squared minus sigma alpha beta sigma alpha beta minus r alpha beta n alpha and beta. I've assumed here that the twist is 0. R is this curvature. Sigma is called the shear and is defined sigma alpha beta is grad alpha and beta minus 1 over d minus 1 h alpha beta. Okay, so some comments here. So first of all, this is there. Depending on the signs of various things, whether things are space-like or time-like or null, whatever, you get different Raychaudhuri equations. The one that I've written here is for a hypersurface orthogonal time-like geodesic congruence. Since that's the situation we're in. So where does this equation come from? This is just a differential geometry equation. I haven't done any physics on this equation yet. What this is it's the equation for geodesic deviation. So I'm sure you have seen the equation for geodesic deviation, but let me just remind you what it is. We have two nearby curves in our congruence, and what the equation for geodesic deviation tells you is you look at the vector connecting 2 points on those geodesics, and then you follow them by an amount delta tau, and you ask what happens to that vector. Okay, so a lot of times the way you learn about curvature is by writing down, is defining it in terms of this geodesic deviation. But you can probably see that the equation for geodesic deviation is, so the equation for geodesic deviation is the second derivative equation, right? It's an acceleration of the geodesics. So that's going to give a second derivative, and that geodesic deviation is going to tell us how much this hypersurface stretches. So if you can, I'm not going to go through the details, but you can see that at least it makes sense that the geodesic deviation equation, when rewritten in terms of a congruence, is going to be an equation for d theta d tau. Okay, because it's a second order. So theta is telling you how fast the volume is changing. Geodesic deviation is a second order equation, so we should get a derivative of theta. And what we've done here is just to recast the geodesic deviation equation in terms of the expansion. Okay, was that good enough? I didn't want to go through the details. I hope it was good enough, because I'm not going to be able to reproduce the derivation. Other questions anyway?
How is this more useful than the usual geodesic equation that we studied?
Because of what I'm about to do. Yeah. I guess you can. It's not, I mean, of course, it's not quite the same equation. The geodesic deviation equation has a vector on the left-hand side. And what I've done here is to sort of dot that into things and to tell you how, not just how a vector is changing, but how the orthogonal area or the transverse area is changing. Okay, so it's the same information, but it's being encoded in a different way. So it's been repackaged. Okay, so the greatest thing about the Raychaudhuri equation is the focusing theorem. So let me state the focusing theorem for this case first, this time-like geodesic congruence. So the theorem is as follows. Well, let me state the theorem in words first, and then we can write it down. Okay, the theorem's going to sound kind of silly when I say it this way. The theorem is that if this term is positive, then the right-hand side is negative. Okay. The first term is obviously negative. The second term is obviously negative. So the theorem is going to say if this term, including the minus sign, is negative, then the whole right-hand side is negative. So let me state that as a theorem. Assuming the strong energy condition so the strong energy condition states that T mu nu minus in 1/2 trace T G mu nu N mu N nu is greater than or equal to 0 for time-like N mu. And the Einstein equation. Okay, so the point is that if you, so usually we write the Einstein equation as relating Einstein tensor to T mu nu, but you can also write it as the Ricci tensor being related to this combination. So you have to you can trace reverse the equation, just take the trace of the equation, subtract it off, and you get that this is equal to Ricci. So if you use the Einstein equations here, the strong energy condition, SEC, becomes R mu nu, and mu and nu is greater than or equal to 0. Okay, so if the strong energy condition holds, and the Einstein equations hold, then the last term in the Raychaudhuri equation is overall minus. So the theorem states that under these conditions, d theta d tau is less than or equal to 0. This has a very natural interpretation. This is, roughly speaking, the statement that gravity is attractive. force of gravity is attractive. So let me just draw a picture of that. I don't know, here's like a planet, a blobby looking planet, and if you if you look at, if you shoot some particles past, then they're going to get bent toward each other. And so it's saying that the force of gravity pulls geodesics together. The acceleration is in the squeezing direction. It's taking, so you have some collection of geodesics, it's trying to squeeze them together as they pass through some energy distribution. Yeah?
Did you assume the cosmological constant is 0 in the answer equation?
Yes, I did. Otherwise, sorry, did I? Yeah, probably, yeah.
I mean,
Well, no, it's in here. No, let me say it's inside the stress tensor.
okay, so we don't have it as like an extra term.
Right, yeah. Okay, if you feel like this was a little bit of a cheat, because I just made up something and I called it the strong energy condition to sound fancy, then you would be entirely correct. Okay, and I'm going to come back to this. The strong energy condition is not true. So the focusing theorem is also not true. Well, the theorem, of course, is true. It has assumptions, but the assumptions are not true. So time-like geodesics do not necessarily focus.
One example of that is the expansion of the universe.
Yes, that's right. The expansion of the universe is a counterexample. I mean, the theorem is still useful because in situations where you can check the strong energy condition, you can conclude that things focus. So the theorem is still useful, but you shouldn't take it as a true statement about the world or about GR that things always focus. So now I want to turn to null hypersurfaces. Null hypersurfaces require a little bit of extra formalism. I'm not going to try to do this in detail. I just want to draw some pictures and tell you the idea. So we're not really going to do justice to null hypersurfaces, but let's see how things carry over. Okay, so a null hypersurface, I'm going to draw like this. So it's null. Okay, and the funny thing about a null hypersurface is that so this is sigma. The funny thing about a null hypersurface is that the normal is also the tangent. Okay, so the normal vectors, the normal vector field lies inside the hypersurface here, and as n squared equal to 0. But just as before, we can define the expansion to be grad alpha and alpha. The interpretation, however, of the expansion of a null hypersurface is a little bit different. Okay, so remember before it was like the fractional rate of change of volume. But now we can tell from the picture that what n is telling us about cross sections. It's telling us about how the cross sections of this hypersurface evolve in time. In other words, we started with a manifold of dimension d. Then we have this null hypersurface of dimension d minus 1. But what we're talking about now is really a D minus is really the evolution of a D minus 2-dimensional manifold. It's going down one dimension. And that's again this fact that the normal and the tangent are the same. You effectively, it's degenerate, so you sort of lose a dimension here. Okay, so the normal vector along this, the normal vector on a null hypersurface tells you about the evolution of something that's 2 dimensions lower. So like if we're in 4 dimensions, then the expansion of a null hypersurface is going to tell us about the shape of something that's 2-dimensional, or the volume of something that's 2-dimensional. In other words, an area, like an S2. Okay, so you can go through all the math, and what you'll find is that it just turns out the same as before, except that it's the rate of change of the cross-sectional area of these codimension 2 hypersurfaces B. I'm not going to prove that, but are we happy with what the statement is? It's not terribly hard to prove. You just have to have a lot of indices, and it actually takes like, it would take me like a few boards to prove it. It's sort of a pain. The problem is that to talk about null hypersurfaces, you have to introduce an auxiliary vector going the other direction as a way of dealing with the fact that this is degenerate. And then you have to kind of go through all this effort to show that everything is independent of the auxiliary vector. But at the end of the day, the equations are just nice and exactly what you'd expect from staring at the picture. Okay. So the Raychaudhuri equation is unchanged. Except that there was a D minus 1 in that equation, and it becomes a D minus 2, okay, because we're talking about a lower dimensional manifold now. And so the focusing, so now I can state the focusing theorem, the null focusing theorem. So the null focusing theorem says that assuming the null energy condition T mu nu, N mu, and nu is non-negative for n a forward-pointing null vector. So assuming the null energy condition, and again the Einstein equation, so that we can relate this to the Ricci curvature, implies null focusing. D theta d lambda is non-positive. Lambda here is an affine parameter along null paths. Okay. Now, same caveats here apply. Well, similar caveats here apply. There's an assumption that goes into null focusing. The null energy condition goes in here. But there's a big difference, actually, between this one and the time-like one, which is that the null energy condition is almost true. The strong energy condition it can be just dramatically violated at the classical level, like in the expanding universe. The null energy condition can be violated, but only by quantum effects. And I'm going to come back to that maybe next time. But for now, just know that this null energy condition is a pretty good assumption. It's true up to quantum effects. So null rays really do focus.
So gravitational lensing is always focused.
Null, sorry.
Gravitational lensing of like light going around.
Yeah. Let's see. Yeah, that's right. That's right.
Yeah, so those are like concave lenses.
Yeah, yeah. Okay, so that's the focusing theorem. And now what we're going to do to derive the area theorem is to apply this to the event horizon of a black hole. First, I need to define the event horizon of a black hole. Well, you all know what it is, but I want to define it carefully because this theorem is completely general. It doesn't even it doesn't assume like any particular metric. It doesn't even assume that the metric is differentiable. It's a very general theorem. So the event horizon is defined as follows. We have a black hole with a singularity. Scri plus is this region out here, this region at infinity. And so let's define a region which is the outside region. So call this region out. So the region out is defined to be the causal past of null future. What does that mean? It means that there exists a causal curve. So that means that so the causal past means all the points in the space-time which you can get to along a causal curve, that is a null or time-like curve. Okay, so like this point here is the causal past because I can draw that curve. But it's just what it looks like. It's like the past causal diamond of everything on Scri plus. Then the event horizon H is defined to be the boundary of out. Okay, this is how event horizons are defined. It's a weird definition. Let's think about how weird it is. Okay, this is things that you hear in a GR class, but let's think about it for a minute. So it depends on what happens in the future. Okay, so it's a global property of a space-time. I can't tell you whether we're near an event horizon right now. We very well might be. I hope not, I guess, but we might be, because we have to know the whole future of our evolution, and we have to have an asymptotic region. Okay, so event horizons are defined from the future. Like you have to go up to the future and ask who can escape there. It's kind of who can escape there. There are other notions of horizon of a black hole. There's the other most popular one is the apparent horizon, which is something that you can detect locally, but it doesn't tell you who can escape to infinity. The event horizon is the true horizon. It tells you who can escape to infinity. So now what I'm going to do is I'm going to take a point here. So now we're going to prove the area theorem. Okay, so let's take a coordinate v, which goes along scri plus, and put a point P of v up here on scri plus. So it's not a point, it's a sphere, right? Every point on this Penrose diagram is a sphere. So P of v is in S2. And what we're going to do is we're going to shoot null rays back from that sphere into the space-time. Okay, so if I draw a picture in space, there's a huge sphere, because this is way up at infinity. So there's some huge sphere, P of v. And on that sphere, we shoot back null rays from all directions. Now the sphere directions are suppressed on the Penrose diagram, so it just looks like this arrow. But this is really a bunch of arrows coming in from all directions on the sphere, converging, coming in to the space-time. Does that picture make sense?
I thought you were shooting away from that point.
Sorry?
Are you shooting them away from the point or towards them?
I'm shooting them away from the point, but back in time, they're being shot into the space-time. I mean, we could reverse the arrows and think of it as them going outward, but it's important that the event horizon is defined up from the future, so that's why I'm shooting them backwards. So we just take all we go up to this point, we shoot null rays backwards, we follow them wherever they go in the space-time, and we'll call those vectors k, which define for us a null congruence. Okay, so we shoot null rays back. From this sphere P of v. And then we take v to infinity.
So those arrows on that sphere are not supposed to be going into the sphere, they're supposed to be going like back in time. Right?
Well, they're going into the sphere. I mean, if you're sitting out there and you want to ask, this is like laser light, okay? So that laser light is coming out at you. So if we draw it back in time, they're going in. But the laser light is going out. It's hitting this sphere at infinity. But yes, they're in space-time, so of course they're also going in time.
So they should be coming out of the sphere then? Instead of going in?
Well, it depends which way we draw the arrows. I was imagining shooting them back. So then I think they should be going in.
But doesn't your arrow sort of indicate the direction of that coordinate v? Because the size of this, these are dictating like the size of the sphere, right? And that is, I think, dictated by coordinate v. It's not.
Sorry, the coordinate v is the coordinate v is that way,
Yeah.
and that's like how long we wait before doing this experiment. That doesn't have to do with the size of the sphere. That would be the coordinate that way.
Ah, I see. Yeah.
See, if we, the coordinate out this way is how big the sphere is. And the coordinate that way is like, do we do the experiment tomorrow, or do we do it like 100 years from now? Now, our goal is to define the event horizon. And so to define the event horizon, the question is, what stuff can ever get to infinity? So this defines this gives you the event horizon. Okay, I'm not going to write a mathematical statement because one has to be a little bit careful with horizons that are singular and stuff like that. But for our purposes, this defines for the event horizon. So we go out to just imagine going out to infinity, waiting a really long time, and then shooting light rays back in time from that sphere at infinity. That's the event horizon. It's not literally the event horizon, because the event horizon is defined in the closure of region out. You know, something in the event horizon, something that's literally on the event horizon never gets to infinity. It just gets stuck on the event horizon. What we really mean is that these null rays get arbitrarily close to the event horizon. And now the area theorem is, we have 2 minutes to prove the area theorem, and it's going to be just the right amount of time. Now that we've got everything set up, okay, so let's look at the congruence. Theta, the expansion is the divergence of k. Now by construction, this goes to 0 as lambda goes to infinity. Because if you imagine sitting on a patch of that very big sphere, then 2 nearby geodesics are just, well, it's basically going to seem flat to you. That sphere is going to seem flat. So there will be a tiny, positive theta if you're sitting far out on the sphere. Okay, so the expansion goes to 0. Then focusing tells you that d theta d lambda is non-negative. I'm assuming here the null energy condition. Sorry, did I say non-negative? I meant non-positive. And we're done. Okay, so let me convince you that we're done. Theta is monotonically decreasing towards 0. Therefore, it's positive. Or non-negative. Okay, just try to picture the function. You have a function that's monotonically decreasing towards 0, then it has to be everywhere non-negative. The expansion is always positive. Now if we want to relate this to the area, so by area, the area of the horizon means the area of these. It means the area of the horizon is a function of time. So this is like each one of these curves is what you think of as the physical area of the black hole. It's a codimension 2 area, or a 2-sphere in Schwarzschild. So the area, we just write d by d lambda of the area of the event horizon is d by d lambda of integral root h, which is integral, so this is an integral over the horizon at time lambda. And we can bring this derivative inside and use the fact that, and relate it to the expansion. So this is integral root h of the expansion, which is therefore non-negative. Therefore, the area of the event horizon can only increase. So this area theorem was, I think, first stated by Penrose, and it was proved by Hawking along the lines of what we just did. A couple of comments. First of all, it didn't assume anything about the details of the black hole. This is true even if you have like merging black holes, crazy things like that. It did assume, however, cosmic censorship. That is, that there are no naked singularities. Where did we assume that? Well, we assumed that everyone on the event horizon. We basically assumed that out was smooth. If there had been some singularity somewhere in out, then there could be some stuff on the event horizon that that was not even near something that made it to infinity. Okay, so we assumed cosmic censorship, but we didn't assume anything else except the null energy condition. Well, the last comment, and I'll have more to say about this next time, is that, of course, when black holes evaporate, when they Hawking radiate, the area decreases. Okay, so the area theorem is not strictly true. The horizon area has to be able to shrink by quantum effects. And that means that quantum effects must be able to violate the null energy condition. And indeed they do. Hawking radiation violates the null energy condition. And that's what allows the black hole to shrink. Yeah?
So one thing that I find slightly mysterious about this is that like Einstein's equations and the geodesic equation are time, like you can send t to minus t. You can send everything backwards in time. So how do you get something that's like not time reversal and variant out of that?
Yeah, it's because of the definition of event horizon. The definition of event horizon broke the time reversal symmetry because it was defined to be the event horizon was everything that can reach scribe plus.
Okay.
If we had defined the event horizon, the anti-event horizon, I don't know, there's no name for it. The anti-event horizon as everything that can reach scribe minus, we would have gotten an opposite theorem.
Okay.
Okay.